we shall continue with the point C of exercise 2. So we basically continue now with basically the operations that we already used in the previous step. The only difference is now we need to show the divergence of omega can be written in terms of our RAM differential in a Hodge star. So we do that, and we just apply our construction based on those operators. And again, we go one step after each other. We have the definition of omega, we apply the Hodge star, we apply D, the RAM differential, and then again we apply the Hodge operator to obtain the final result. So we just need to go one step after each other. So as before, we just start with our one form, which is this one. I already seen that. And now instead of applying D, we apply the star to it. So we're going to do the same. And before, D was going to work on the operators, sorry, on the coefficients. Now, because it was a derivative, now our Hodge operator is going to work on the one forms, so the theta. Therefore, our star is going to work here and here for one component and the other component of omega, of our one form. Then what we do, we just use the results that we have from our previous steps, because we already applied the Hodge operator to the theta, we already applied to the phi, and we just plug it in. And that's the final result, okay? So that's we get. Then what we do, we apply, we are basically in our chain, we are here. Now we apply D. We apply D to this operator, and again, D is going to work on the scalar part, because it's just a derivative, right? Therefore, we are going to have D applied to this, and D applied to this. So it's only working here and here. Again, keep in mind that D applied to the scalar gives you a one form. Combined with another form, since we are working with antisymmetric structures, we are going to use this operator in between the bases, okay? Just to keep the antisymmetry working. Then what we do, we just use the definition of D, as we did earlier. Therefore, we're just going to compute derivatives. So we are going to have the derivative of our scalar function, and we're going to have the basis, the theta. Remember that we have a symmetry, because this is the definition. So we have derivative and basis for all the components of our two-dimensional space in this case. Therefore, we have the derivative with respect to phi, and then we have derivative with respect to phi of that, but that's equal to 0, as we know. Then we are going to have, for this other part, the derivative with respect to phi, and the derivative of respect to, of theta, sorry, and the derivative with respect to phi. And again, this derivative is non-zero, but here we have repeated indices, therefore that's equal to 0, and the only terms that survive are those two. Then we just compute the derivatives. We flip these two guys as we did earlier to put them together outside our parentheses. And this is what we get. So just apply derivative, flip these two guys to group them together outside the parentheses to have a better expression. Done. Next step, so we are arrived at the application of D. Again, we need to apply the Hodge star operator to our final results. So we just do that. We have D, we apply it to all of that, and D goes, boom, goes down to the basis, because that's applied to the one forms, not to the scalar. It's transparent with respect to the scalars. And therefore, we are going to have our D star of this guy, but we already know, because we computed before. And then it's just a matter of making the products, the sinuses and cosinuses, and this is going to be our final results that, oh, look, is exactly what we were looking for. This guy.